All right, stop having fun. It's time for math. For me, yeah. I love it. That's on the recording, by the way. So now everyone gets to hear me diss math. I love math, I swear. Okay, so last class we basically introduced vectors, right? We spent the whole class talking about vectors and the geometry of them and how to manipulate them a little bit and that sort of thing. So we're going to continue a conversation about the properties of vectors, and then I want to talk about a couple more operations that we would care about when it comes to vectors, namely the dot product, and obviously, you know, we're saying we have this concept of length, but we haven't actually discussed how to find the length, although it's what you would expect it to be based on how things work in R2. So I'm just going to write down some properties real quick. And, you know, we're starting off with a real banger. It's just the properties that let us do algebra with vectors. So let U, V, and W be vectors. And let's let C and D be scalars. Then there's just a bunch of properties. And most of them are exactly what you would expect. Like, again, none of these are surprising. So if you add two vectors, it doesn't matter which order you do them in, right? That's commutativity. If you add three vectors, you can essentially drop the brackets, which we've talked about before. So U plus V plus W. Especially when we start talking about abstract vector spaces. We don't do that, but I mean, in terms of math, this is where these properties start to actually disappear, right? I've mentioned these are things that we know happen for numbers, so why write them down? Well, when we start talking about matrices, this one doesn't end up being true. And then when you go into some abstract vector spaces, neither of these end up being true. So they actually do need to be written down. We can't just pretend they're true all the time. And that's associativity. This one, though, is always going to be true. If you add 0 to a vector, you get the vector back, right? It just doesn't do anything. That makes sense. Similarly, if you add a vector to its negative, you get the 0 vector, obviously. That makes sense. When we want to multiply vectors that are being added and multiply by constants that are being, or not constants, scalars that are being added, they work how we would hope. So in words, that's a lot, but in symbols, it makes sense. So if you have two vectors being added together, this scalar distributes, right? You can add the vectors first and then multiply, or you can multiply the vectors by the scalar and then add them, right? It doesn't matter which order you do them in. And similarly, if you have two scalars, you can add them up first and then multiply the vector, or you can multiply the vector by each of them and then add the result, right? It works how you would expect. These are called distributivity. Another one sort of related, if you have two scalars, I mean, this is just how multiplication for numbers works, right? You can, you know, do them in separate orders. This basically just tells us we can pull numbers out of vectors just fine, right? There's nothing shocking there. And another real shocker, if you multiply a vector by 1, nothing happens. Right? So these are all basically just saying algebra with vectors works how you would hope, right? There's no surprises or twists here. So again, the reason why we would even bother with talking about this is now we can do algebra. So simplify with quotes around it, of course. The expression, so it's just a mess. For U plus 1/4 V plus 5U. Right, so this is, I mean, we could go into the nitty gritty of using all of these individually, but the point here is that the algebra works how you would expect, right? So we don't have to do anything fancy. We can just say like, well, we know this number distributes in just fine, right? So this is going to be 4 times u plus 4 times 1/4 u, or 1/4 v, plus 5u. Okay, but we know that these just cancel each other out. And now because we can freely swap addition around, then we can just combine like terms for addition, right? So we've got a 4u and a 5u, so that would be 9u plus v. So there's some properties here that are being used that are being swept under the rug. Like this one here technically uses this, and then you get 4 times 1/4, which is 1. So then we're using that property. But like again, everything works how you'd expect, right? So we don't have to write an intense amount of information down to actually work with this. But of course, the reason why this is usually used is for solving equations, right? That's generally speaking, when we have algebra, we use it for a purpose, which is generally that. So if 3a minus 2b equals minus 2, or sorry, not equals, that's bad, minus 2b minus x plus b minus 4a. So this again is another perfect excuse, because in linear algebra, manipulating expressions that look like this is the bread and butter, right? So this is me saying, hey, we're going to do a lot of this, so get comfortable with manipulating linear equations. So like simple stuff like this, is there's just numbers and variables, right? So we want to solve for x, right? Which is a vector in this case, not a number. So that's an important distinction to remember, right? Remember what you're working with. So, okay, we just deal with this expression. So we can multiply this 3 in and get 3 times a minus 3 times 2, which is 6. Then we've got this minus 2, which we multiply in, minus 2 times b. Minus 2 times minus x becomes plus 2. Yep.
What is after x on the right side of equals?
This? Oh, that's plus. Sorry, write like a child. Is that the one you meant?
Yeah, plus b minus what?
Sorry, minus 4a. So we distribute this in, minus 2b, minus 2 times minus x becomes plus 2x equals x. This doesn't really change. Now, when we're trying to solve for one particular variable in an equation, we move everything else to one side. We isolate the variable that we are interested in, right? So we isolate the x. So let's move the x over here and all this other stuff over there. Now, again, I've mentioned in the past, moving stuff over is a bit of a misnomer. What we actually do is we subtract x from both sides. That's what's really happening. To move this over here, we add 2b to both sides and add 6b to both sides and subtract 3a from both sides. If that helps you conceptualize it better, but we're just going to do the shorthand here. We're just going to move stuff over. So we move x over, which 2x minus x. Now we move all this over. So we've got, I'm just going to not simplify it in my head, because that's a recipe for mistakes. So we've got this, which we left alone, and then we're going to move all this stuff over. So minus 3a plus 6b plus 2b. And now we combine everything. So b, 6b, 2b, so that's 9b. Minus 4a minus 3a is minus 7a. Right, so then that's the solution, right? The solution is, well, whatever a and b are, this combination of them gives us x, right? That's how we solve for it. So the point here is that nothing is different from how we would do this with just numbers, right? It's just now these are vectors rather than numbers. They represent something different. So the reason why we care about doing this sort of manipulation is probably what is one of the most important definitions in linear algebra, which we'll touch on a little bit, but not too much, because it's getting into the real theoretical nitty gritty of linear algebra, but we care more about the mechanics. But it's still something that's going to come up. So that is the idea of a linear combination. A vector u is called a linear combination of a bunch of other vectors. Let's call them v1, v2, v3, and so on. There's k of them. So however many we want, doesn't really matter. Yep.
So how is it being combined with other vectors?
So linearly, right? Linear means add and multiply scalars. So I'm going to get to that, right? I have to write it down. So a vector u is called a linear combination of these vectors if there are scalars c1, c2, c3 up to ck. So that v, or sorry, u, I guess, the vector we're interested in is a linear combination of those vectors. So linear means we don't have anything like sine or squaring something or anything like that. It's just number times variable or number times vector. So c1, v1, c1 is a number, v1 is a vector, plus c2, v2, plus c3, v3, ck, vk. So this, again, I've been mentioning it, but in linear algebra, these are just what the definitions look like. You just have to get comfortable with this. Both for linear algebra and honestly, a lot of algorithms and methods you'll run into in programming look like this too. It's just things are indexed this way with subscripts. So you just kind of, it starts to wash over you after you see it enough. Let's just do some examples. Because I think when we're talking about a definition with a bunch of variables and symbols in it, it's best to just actually write one down so you can see what it means. So the vector 2 minus 4 is a linear combination of the vectors 1, 2, and 0, minus 2, because, well, we're going to call this our u. This is our v1 in our definition, and this is our v2. If we're saying that u is a linear combination of those two vectors, that amounts to finding the numbers that go in front here. So we're saying u is equal to c1 v1 plus c2 v2 for some scalars c1 and c2. So let's unpack what this means, right? We've written it down in symbols, but we actually know what these vectors are. So u is 2 minus 4, and we've got this c1 that we need to find times 1, 2, plus c2 times this thing, which we gotta find, right? Okay, well, this one, so we're gonna develop methods on how to do this, right? The whole point of linear algebra is to deal with this, but we can sort of condense this, right? This left-hand side stays how it is, 2 minus 4. But then we can multiply this in to get c1, 2c1, plus 0, and minus 2c2. Right, this comes from, we multiply the scalars in, and then we add them up, right? But now this is two equations, two unknowns, which we can use regular old methods to solve that, right? So two equations, two unknowns, which if you remember your high school stuff, that means there's either no solution, like there's a couple of situations you could get, no solutions, you could get a unique solution, or it could be an overdetermined system of equations, which means you could have infinite solutions. So let's just see what we get. So this is saying the first equation is that I'll write the plus 0 so it matches exactly. Minus 4 is equal to 2c1 plus or minus 2c2. So this automatically tells us this first equation, divide by 2, c1 has to be 1, right? Okay, so then that means this tells us we can plug 1 in. And now we move this over, minus 6 is equal to minus 2 c2, so c2 is 3. So that tells us what numbers go in front. Yep.
Why is 2 equal to 2c1?
Because I can't read my own writing, apparently. Thank you. See, I like making mistakes not on, I mean, I don't, but it means at least I can tell that someone read what I wrote. So thank you. Yes, this should be 2, which means we plug 2 in. And so this is 4, this is minus 8, which means when we divide by this is 4 to C2. Thank you. But the point is now we found these numbers, right? Our goal was to find the numbers that went there. Now we know it's 2 and 4. So let's actually check that, right? This means U is equal to 2v1 plus 4v2. So is it the case that this is true? Plus 4, 0, minus 2. So, okay, well, the first one is good because this is going to be 2 plus 0. All right, good. Matches. And this is going to be 2 times 2, which is 4, plus or minus 4 times 2, which is 8. So 2 minus 4, which is what we wanted, right? So that's all linear combination is for a vector, right? It's just, hey, what numbers go in front of all the other vectors so that when we add them up, we get the vector we're interested in. That's the punchline. It's just find these numbers. So if a question asks, is this vector a linear combination of these vectors? Then the answer is, well, I don't know. I have to see if I can find these numbers, right? Either I can find them or I can't. If you can find them, then that means it is a linear combination. And if you can't find them, by which I mean they don't exist, not I struggled with the question and couldn't find them, then that means it isn't a linear combination, right? Okay. So we're going to come back to that definition. It's just it fits naturally in when we're talking about, vectors and yeah.
Why is it c minus 2c2?
C minus 2c2. Where did I put that?
Right. I think it's a fraction.
Oh, because it's c2 times minus 2 here, right?
Yeah.
So then you could simplify this to write minus 2c2 if you wanted. I just was copying directly. Yeah, that's all. You don't have to I think most people would naturally write that as minus, like just in their head. I just wanted to, copy very directly down like that. So either is fine. Okay, so we'll come back to this when we develop better techniques. Ultimately, linear algebra is dealing with stuff that looks like this. Well, yeah, it's dealing with stuff like this, but everything boils down to this. And by everything, I'm not even kidding. My graduate thesis, which was in representation theory, vector valued modular forms, and a bunch of number theory stuff, don't worry about that. Point is, like high-level graduate mathematics, when I actually finished figuring out my problem, it boiled down to solving stuff like this. So even really high-end mathematics in linear algebra is like, oh, well, I found the path to get to this, and now I just have to do my usual stuff. So this stuff comes up a lot. And again, if you have any passing interest in working with large data sets or AI algorithms, you're going to need to know linear algebra. It's unavoidable. But we're just going to talk about some other operations we can do on vectors. So, we've said that vectors have sort of a direction and also a length, but we've only visualized the length. Normally, we would like to numerically represent the length, right? Because if I can draw a vector from me to that window, I would like to know how long it is in terms of a number, instead of like how many meters or whatever, right? So we need to sort of capture that, right? How do we capture length? So the first thing we're going to do is talk about dot product. So if, and again, you you get used to this, and I'm writing down a bunch of it so that you just get exposed to it. So right now, when you start looking at the linear algebra notation, if you're overwhelmed by it, that's totally normal. So we've got two vectors in Rn, because it doesn't matter what dimension we're talking about. Then the dot product U and V is, so we use a dot, so it's called the dot product. All it is just we multiply these components component-wise and add them up. So we would do the first one times the second one plus the second one times the second one plus the third one times the third one all the way down, right? So it's going to be U1 V1 plus U2 V2 plus U3 V3 and so on until you get to the end, UN Vn. Now, I've said that there is no meaningful multiplication of vectors. And so you might look at this and be like, oh, Travis, that's multiplication of vectors. No, it's not, because we took a vector and did this operation and got a number. We did not get a vector out of it. And if we were going to meaningfully define multiplication, then we would need to get a vector out of it. And again, I don't want to get into the nitty gritty. And you'd say, okay, well, why don't I just do that to define multiplication for vectors? Why don't I just, multiply all the components? That ends up not working very well. It doesn't end up doing a lot of the properties of multiplication that you would hope it would. So it doesn't end up working very nicely. So ultimately what I'm getting at here, I'll write it as a warning, U dot V is a number, not a vector. So that means if you do the dot product and get a vector out of it, you did not do the dot product correctly. That is a common mistake, and I get it, because the notation does look sort of like multiplication, except the difference is, like, we usually very, very deliberately, like, make a dot. Whereas, like, for multiplication, you might just write the numbers next to each other or not write a dot, really. But this is like, no, it's a big, big dot. But that's all there is, all right? It's just you basically go component-wise, multiply them together, and then add them all up. So as an example, can't spell. So let's let one vector be, all right, it doesn't even matter. I'm going to read that. And V is 1, 2, 3. Doesn't matter. So then U dot V, what do? We just multiply them component by component and add them up, right? So minus 1 times 1. Now this is regular multiplication. 3 times 2 plus 4 times 3. And if you don't want to confuse yourself, it's not uncommon to write it like this. Put like the first number in brackets so that you know it's multiplication, but don't put the dot so you don't get it mixed up. Either is fine. Whatever you want to write, it's all good. And honestly, once you get comfortable with the dot products, people just are able to do it in their head usually. So this is minus 1 plus 6 plus 12. So that's 17. I went to check to make sure I had the right answer, and then I realized I wrote down completely different vectors. Okay, so this operation here also has some properties, and ultimately they end up being pretty nice too. So, and we kind of envision them. So if you did u dot v, that's going to be the same thing as v dot u, because I mean that's how multiplication works, right? And that's all we're doing. We just swap the order of these. Doesn't matter. So okay, obviously that's true. It does behave nicely with addition. So if you're taking the dot product of the addition, you can instead do the dot product first and then do the addition. Again, it's important to remember here, the addition we're doing is vector addition. These are two vectors being added up. Over here, we're adding numbers, right? The result of the dot product is not a vector. It works nicely with scalar multiplication too. So if you have a vector scaled by a number, I'm going to like this. So some vector times a number, you can instead just pull that number all the way out and do the dot product first. So that's especially nice for fractions, right? If you notice everything in a vector is like 1/2 or like some number over 2, pull the 1/2 out and deal with it at the very end, right? Just deal with nice looking vectors and then divide it by 2 at the very end, right? Because it's probably going to be an integer anyway, so you might as well save some effort. One that ends up actually being really useful when we want to start talking about length is what happens if we take the dot product with a vector in itself. Well, it's always going to be bigger than or equal to 0 if we think about it. If we just replace this with the same thing here, it's going to be u1 times u1, which is u1 squared. It's a positive number. Right? And then we just do that for all of them. So these are all squared. So we get a positive number, or it could be 0. Yeah.
That sounds awfully similar to the Pythagorean theorem.
So there are connections between, yes, it's called, we don't call it the Pythagorean theorem in linear algebra. It's the triangle law or something like that. But yes, it is very similar. So when is this equal to 0? Only in one case. If u is the 0 vector itself. So this will always be a number bigger than 0 unless the vector itself is 0, which is really nice to know, right? That means if you're sort of building an algorithm or something that involves the dot product and you want to exclude the 0 vector, well, if the dot product was 0, it had to be the 0 vector. So you can skip some steps there. Okay. There's a bunch of proofs in here which we don't really need. So I'm going to use this, though, essentially to define the length of a vector. Because we're here to talk about dot product and length. So fortunately, we can leverage this property. So the length of a vector which we denote with these double lines like that. We also call it the norm sometimes. Is given by, it's the square root of u dot u. All right, we're just using this dot product here, which is nice because we know how to compute the dot product and we know how to compute square roots, right? And this is a valid thing to do because we know that u dot u is always at least 0, right? It's never less than 0. So we're not going to take the square root of a negative number here and have to worry about that. Okay, but let's expand this a little bit. So we've got this square root coming along for the ride, but what is this? Well, if we think about it, we're doing u1 times u1, which is u1 squared, plus u2 squared, plus all of them squared like that. Now, this looks very, very similar to a formula that you've probably seen in high school, which is namely the distance between 2 points, which is normally framed, there'd be like some subtraction there, which is pretty nice, though, because we can connect those two concepts. But let's just do an example first, just to dot our I's and cross our T's. So let u equal whatever, 5 minus 2, 1. Then, what is the length of u? Well, it's just that dotted with itself, which means you just look down this list and square everything, right? So 5 squared plus minus 2 squared plus 1 squared. Remember, if you're squaring minus 2, it's this and not this, because we are doing minus 2 times minus 2, not minus 2 times 2, right? It's important to remember that. We have to that's why I look at this vector and I think in terms of just going along the vector, right? 5 times 5, minus 2 times minus 2, 1 times 1, right? And then you won't make that mistake. So the length is 25 plus 4 plus 1, which is square root of 30, which is, who cares, right? It doesn't really matter. Because ultimately the point of lengths is to compare them to other lengths. So you can ask, well, what unit is that? Who cares? The unit doesn't matter, right? As long as they're the same, right? Square root of 30 is a bigger number than square root of 2. So square root of 30 is longer, right? No matter what that unit of measurement is. In fact, it's 15 times longer. Okay, so there are some properties here too, which again, none of them will be surprising. And ultimately they just mean that, hey, this length thing, it works how we would hope it would for a length. The first one, the length is bigger than or equal to 0. Which, why is that true? We don't even need to think about it. We define this in terms of the dot product. That's a property of dot products. So of course it's true here. Same thing, same exact result. The length of u is 0 only when u is 0. Again, same exact property. But a new one is if you have a vector and you're multiplying it by a number, how does that affect the length of it? Well, it's is c times the length, but we have to take the absolute value, right? Because c could be a negative number. If you're saying, okay, minus 2 times u, well, it's not minus 2 the length, right? We don't have a negative length, so we have to take the absolute value, which means just drop the minus sign. Okay. So the connection here, and why we care about giving a number to length is because then we can compute distances, right? If we've got 2 things in space, we want to know how far apart they are. So the distance between vectors u and v is given by, well, the whole point here is the leverage stuff we've just talked about. So the distance between 2 things is just the length of u minus v. So if we think about it, let's draw a picture. So we've got, I need my colors. Well, no, I don't. So we've got this v, and then we've got some vector u, right? So what is u minus v? Well, again, remember we draw v in the opposite direction, and then we create the parallelogram. and this is u minus v. But one thing that we're free to do here is we can take this vector and we can move it however we want, right? Specifically, we can pick this thing up, which my picture isn't super accurate. I have one in the notes that's more accurate. We can pick it up and move it over here, right? Which is exactly what we would think of when we talk about distance, right? What is the distance between this point here where v ends and this point here where u ends? Is the length of this line segment, right? Which is what we just found, right? The distance here is the length of this line segment. So this actually matches up with our intuitive definition of distance. And if you recall the formula in high school for distance between 2 points, so from high school, distance between let's call it x1, y1, because you would have talked about it in R2. X2, y2 is the square root of x1 minus x2 squared plus y1 minus y2 squared, which is exactly what this definition here is, just for things higher than R2, right? And remember, we have a correspondence here where if we start at the origin, a vector and the point it points to are the same thing. So that's why these definitions also match up. So there's a lot of connection here between stuff that you've already seen and us just sort of generalizing it, which again, that's what we like to do in math. That's kind of the whole reason why we talk about math, is because we've got these things that we know and understand very well and ask ourselves, how can we generalize that, right? How can we generalize it and abstract our thinking about it? So in this case, we looked at this concept of distance between 2 points just in the plane and said, okay, well, can we get that same exact idea for vectors? And yeah, okay, we did, but do they match up, right? If we just sort of abstracted something and generalized it and then bring it back to where we started and they don't match up, then it's a stupid definition, right? So the fact that these two ends up being the same thing is good. So as an example, we're just plugging numbers in now. So let's let u be 1, 3, minus 4. And okay, I chose very specific numbers here, so I'm just going to roll with them. A vector v is 1 minus square root of 3, 1 and minus 1. So when you're dealing with vectors, you actually end up seeing square roots a lot in them, unfortunately. But let's talk about the distance between these. Distance between u and v. Well, that's the length of u minus v. So first we have to find that, and then we find the length of it. So what is u minus v? So you can do it on the side or in your head. It's 1 minus square root of 3. 3 minus 1 minus 4 minus 1, or minus 1. So that gives us that we need the length of 1 minus 1. Those go away. The minus 1 goes in there and becomes plus square root of 3. 3 minus 1 is 2. Minus 4 plus 1 is minus 3. So this is more just an example of like, hey, sometimes you get minus signs and you need to... Honestly, the number one mistake in linear algebra that students make is that sort of stuff. Just missing a minus sign, or you have like 2 plus 4 and you write down 7 or something. Like it's so easy to do stuff like that. I do it all the time. I'm not even going to pretend. But now all we need to do is we just plug into this formula. So this is the square root of 3 squared plus 2 squared plus minus 3 squared. So that's square root of 3 plus 4 plus 9. So that is 12, 16, which is 4. Hey, we got a whole number out of it. That's kind of the thing about distances between vectors is usually if you want this thing to be a whole number, somewhere in here has a square root, and vice versa, right? Like it's only really boring vectors have distances that are whole numbers when these have whole numbers in them. So okay. Earlier we talked about what it means for vectors to be parallel, right? Two parallel lines. They can be on top of each other. But there's a similarly related concept when we're talking about line segments or lines. We've got parallel and then we've got perpendicular, right? Lines can be either parallel or perpendicular or neither. They don't have to be either to each other, right? Like perpendicular means 90-degree angle, so that would be perpendicular. But then something like this is neither, right? It's just two lines. So we already have this definition covered. So let's cover this one. It's fortunately very easy. So two vectors in Rn are called, so we're going to write the familiar term first, perpendicular, or orthogonal, if, well, it's just, if you take their dot product and you get 0. Right, it's really easy to find. So, for example, are these two vectors orthogonal to each other or perpendicular? Well, no, because we've got that square root of 3 in there, right? So, like, if you imagine taking the dot product here, nothing cancels out that square root of 3. So it's at least not 0, so they're not perpendicular to each other. But let's actually think here. So let's draw two vectors. Say this is 2, 2. And so then we would have, I'm going to shorten that. So that'll be 1 minus 1, right? This obviously has a 90-degree angle between them, right? But if we just look at that, we would say, yeah, these are perpendicular to each other, right? So does that match this definition we just made? Let's make sure of that, because again, if we're going to sort of take a definition that we know and are familiar with and generalize it, better still match up with the original. So let's call this one U, and let's call this one V. So what is U dot V? That's going to be 2, 2, dot with 1 minus 1. So that's 2 times 1 plus 2 times minus 1. So that's 2 minus 2 is 0. So indeed, this definition at least seems to match up with the intuitive definition of what it means to be perpendicular or orthogonal. Now, the reason why we have, that's perpendicular. So the reason why we have two different words here, ultimately, so in math, like over here, where was it? I erased it. We had another definition where we changed the length or norm is what we said. Part of it is because the idea of being perpendicular sort of really depends on being in like 2 dimensions, sometimes 3 dimensions. You can talk about perpendicular lines in 3 dimensions too, although you can kind of rotate the line around it so it makes a little bit less sense, but still matches up. But when we're talking about higher dimensions where we can't even visualize it, that's ultimately why we come up with new words for it, because we want perpendicular to still mean that very specific, intuitive geometric idea, and we don't want to start conflating them, because then if someone says like, yeah, they're perpendicular in R5, you're like, the hell, that doesn't, I don't know what that looks like. But if I say they're orthogonal, you're just like, oh, orthogonal means this, right? It just turns out that they match up in 2 dimensions. And same thing with length or norm, right? We have this thing called norm. We talk about that when we're talking about vectors in R7 or whatever. It just turns out that that concept also matches up with the intuitive definition of length when we talk about vectors we understand. So no, we don't just invent new words in math because we like the smell of our own farts or something like that. We do it because we actually, it's funny, we want the opposite of what it ends up accomplishing. we want to come up with different words so we don't confuse people. So that when we say this word, we're talking about this. When we say this word, we're talking about this intuitive 90-degree thing. But for most people, when they're learning it, they're just like, so there's two words for the same thing? I'm confused. Which, you know, no one ever said mathematicians were good at like being friendly, I guess.
Making things intuitive.
Yeah. Yeah. It's one of those things where I've just become so used to it that I don't even think about it. But I get it. That like, you know, I can say that as much as I want, and then students hear that and they're like, doesn't help me, Travis. And I'm like, I know, sorry. But that's why I always try to write down, I will write down both words, and I'll, especially when the concept is new, I'll say both out loud so that you can draw that connection. Because that's how I learned it, right? Like, how did I learn all of this? Turns out I wasn't born with the idea of what orthogonality is. It's just someone taught it to me by saying it over and over and over again, and then it just eventually, it was like, okay. Okay, so that does a good job of covering what I want to talk about for the geometry side of things for at least a little while. The very, very end, hopefully, I'll have time to at least talk about. It won't be on any assessments or any assignments or anything like that. It's just if we have time, we'll talk about it. Linear transformations, which is the real reason why someone would care about linear algebra for like computer graphics and stuff. So we're gonna put this aside for quite a while, and we're gonna start talking about the algebra side of things. So, intro to linear systems. And this is where the notation starts to get overwhelming.
I already did.
Well, yeah, and I'm saying that, so buckle up. But again, I'm trying to, you know, the notation can be a lot, but then the example sort of drives home that, hey, the notation looks bad, but the concept isn't. And this is going to be kind of similar. So a linear equation is exactly what you would expect it to be in the n variables. X1, X2, n of them is of the form. Well, all it is we've just got some numbers in front of those variables. To x2 plus an xn is equal to some number, right? I'm going to use B, actually. Alphabetical. Hey, this sure looks like a definition we wrote down previously, right? We had this, except for linear combinations, where these were not variables, they were vectors. And this was a vector, but it's the same kind of concept. So when we say linear, well, the equation part of here is obvious, right? We've got two things on the side of equal signs. So that's equation. Linear means exactly this part, right? A number times a number plus another number times a number plus, that's it. The things that we are doing are we are adding numbers and multiplying numbers by other numbers. No other more complex operations. That's what linear means. So these numbers here, the A's that go in front here, are called coefficients. These are obviously called the variables, and this is called the constant term. Now, again, this notation is spicy, but let's write down some examples and you'll be like, okay, yeah, no, that's from high school. So something that looks like this. I guess I don't need to look at this because it's easy enough to write them down. So like 2x plus 3y minus 7z is equal to 2, right? That's a linear equation, right? Because it's a number times a variable plus a number times a variable minus a number times a variable equals a number, right? Linear. Something that doesn't seem linear at first, this isn't division, I'm just, let's do this. It's something like pi x1. So pi is a number. That's fine. Minus square root of 3 x3 is equal to 1. Square root of 3 is just a number, right? If we had done this, and it was square root of 3x3, now we have a problem. That's no longer linear, right? Because we're doing a different operation on the variable itself. So as long as it's outside of the variables and that variable is just by itself, nothing fancy happening, that's linear. So some not linear equations. So the most common things to make equations not linear is an example of what I just did there. So we could do like square root of 2x. Now the square root is over top of the x. That doesn't work. Yeah.
And they're called linear because when graphed, they just come out
As a line. Yeah. Or well, in this case, this would be a plane, but they're flat-ish surfaces, right? They don't have any curvature.
Will they be called planar equations then?
Well, no, because linear has a specific meaning. It's constant times variable added together with others. So no, we would call it linear. But I would call this the equation of a plane. Yes. So then we've got sine of y equals 3. So again, not linear, right? Because we've got the square root of 2x, and we've got sine of one of the variables. That's a nonlinear operation, right? Sine is some curvy thing. Another example that would remove linearity is variables times variables. Right? These are interesting in their own right. Like they give us surfaces and graphs that are interesting and powerful in calculus and stuff like that. But that's not what we're interested in, right? We don't care about this stuff. The reason why is solving these equations is hard, generally speaking. When they start to get complex enough and involve enough variables, you're down to numeric methods. There isn't even an algebraic way to solve most of them. But linear equations are really nice because the method that you would have learned in high school, where you isolate one of the variables and then substitute that variable into all your other equations and rinse and repeat, will work no matter how many variables and equations you have, right? It'll always work. So it's a terrible way to do things because it gets really messy really fast, but it will always work. Whereas these, you need different techniques for different forms of them. So what we're interested in linear algebra is solutions to linear equations. So a solution to a linear equation is a vector. What do I call it? I don't even give it a name, I don't think. I'll call it S. S1, S2, up to Sn. So it's a list of numbers such that, so you've got that equation written right here. If we plug it in for the variables, an, Sn, it works, right? So solution means what you think it means here. Means plug numbers in for variables, and it works. So as an example, I'm going to copy down this equation so I don't have to solve any of these. Well, actually, this one's pretty easy. So let's look at this. 2x plus 3y minus 7z is equal to 2. 1, 0, 0 is a solution. So what does that mean? It means if we plug these numbers in for the variables, minus, we better get 2. Right, so 2 times 1 is 2, plus 0 equals 2. So it worked, right? That's all we mean by solution, right? It's just something that we can plug in and it works. Okay, but linear equations on their own aren't terribly interesting. So what we're interested in fact, is systems of these things. So a system of linear equations is just a bunch of linear equations taken together. It's a set of linear equations in the same variables. So, if you had x, y, and z, then you've got, those are the variables that all of your equations involve. So a solution to a system of linear equations. Eventually, we're going to drop the phrase linear equations because we'll just assume everything is linear. So we'll just say a system of equations. Is kind of what you would expect it to be. It's something that solves all of the equations involved in that set simultaneously, right? So if it solves one of the equations, it needs to solve all of them at the same time. They all better be true. Solves all equations simultaneously. And the solution set is all the solutions. So, okay, let's take a look at an example here. So let's consider and this will show you what I mean by system. 2x1 plus 3x2 equals 0. x1 minus x2 equals 1. So when we say system, we mean this whole thing taken together, right? If x1 and x2 are valid solutions to this first thing, we better be able to plug them into the second thing and get a solution also. So, finding solutions to this thing is a bit annoying, so I'm just going to have to read my note here. 3 over 5 minus 2 over 5. I'm going to make that bigger. Let's see if this is a solution. So 2 times 3 over 5 plus 3 times minus 2 over 5. So let's figure this out. 2 times 3 is 6 over 5. 3 times minus 2 is minus 6 over 5. So 6 over 5 minus 6 over 5 is 0. Okay, good. It solves the first equation. What about the second one? So that's 3 over 5 minus negative 2 over 5. So 3 over 5 plus 2 over 5 is 5 over 5, which is 1. So it works for both equations, right? Awesome. So is a solution. Okay, but now if I just write down something random, because spoilers, all the solutions are going to be multiples of this. Let's see, is this a solution? So 2 times 1 plus 3 times 2. So that's 8, which is not 0. So already we don't even have to keep going, right? Because it has to solve both equations. It didn't solve the first one. Who cares what it does to the second one? So is not a solution. And it has to work for both. Okay, now, real quick, these types of things here, these objects, who remembers these from high school? Like equations like this? Just seeing it at least, not how to do it, just like, see, maybe you would have seen X, Y, Z rather than X1, X2, X3. Okay, that's fine. We're going to talk about the techniques for how to solve them. Or you know what? That technique doesn't even matter because we're going to talk about a better technique anyway using linear algebra techniques. So don't even worry about it. You can, if you don't remember it, then that's okay. You don't have to know the bad method. So there's a couple words that we throw around a lot. So a system of linear equations is called consistent if it has a solution. At least one solution. So that means this thing right here, we would call it consistent. Why? That's a solution, right? Are there more? Who cares? The definition just says there's one, at least one, and we found one. So a system is called inconsistent if there isn't a solution. These words are there just because saying it has at least one solution is a mouthful, and it comes up often enough that we just gave it a word, right? It's called consistent. Just means at least one solution. Inconsistent means can't solve it, right? Again, not I can't solve it in the sense of I'm struggling to solve it. It means no, there's none. It's impossible. You can't solve it. So let's look at an example of one that has no solutions. So we're going to look at, I guess I'm going to do this. I don't need to look at that. Equals 0. So same first equation as that. And 2x1 plus 3x2 equals 1. So without even really doing any algebra here, this is not possible to solve, right? We have to have a choice of two numbers that when we plug into this equation, we get 0. But also, if we plug those numbers in, it better give us 1 also. Like that's not possible, right? So we can't have 2x1 plus 3x2 equals 0 and 2x1 plus 3x2 equals 1 at the same time. So this system has no solutions, even though these equations on their own both have solutions, right? We can solve these just fine, but they don't have more than one. Right? It doesn't solve both of them. System is inconsistent. And again, because there's a lot of terminology, whenever it comes up, especially at first, I'll just remind you what it means so that you don't have to, dig through notes or whatever. What time is it? Okay. Do I want to say this? Yes. So a system of equations, we're going to drop the linear because everything here is linear. We don't care about anything else. Has either of the following three things, and it is exclusively one of them. No solutions. So like this, right? It wasn't possible to solve this. Exactly one solution. So the example we just did, actually, the one before this, has exactly one solution, that fractional thing. And then there's one more possibility. So, there's no solutions, exactly one solution. Well, what if there's like 5 solutions? It turns out it jumps immediately to infinity. So infinite solutions. One of these three situations is true. So what that means usefully from this is if you found two solutions, you automatically know how many there are. It's infinite. There's a lot more that you could plug in that would work. The technique we use to solve these systems will expose that information anyway. It doesn't really matter, but it's just if someone said, hey, these are the two solutions to this system, you'd be like, no, there's way more. You missed infinity of them, in fact. But this is just a useful fact to know. So, I guess really quickly, how do we solve these systems? So, okay, we do something called solving for isolating variables and then back substitution. For variables, and then what's called back substitution. And let me see if I have an example written down that I can steal from, because now I'm deviating from the notes. Because everyone's like, I don't have a recollection of solving systems of equations. And I'm like, okay, we should actually probably do one the old way then. This one looks like it should be good. So let's solve this. And this is probably the last thing we'll do today because I'm going to show this way of solving a system of equations, and then we'll develop a better technique that is much nicer to work with. So let's solve the system 2x1. I often like to do this notation for reasons that you'll see why, like I'm skipping a gap there. And then we'll have x1 minus x2 because that's where the second variable would go and there isn't one there. Equals 1. 3x2 minus 2x3 equals minus 1. So this is 3 equations, 3 unknowns. So any of the situations could come up. We could have no solutions if these just don't make sense. Basically, if these equations contradict each other, we could get exactly one solution if there's exactly enough information to solve an equation here. Infinite solutions would mean one of these equations doesn't tell us anything, right? It's extra information and we don't need it to solve our system. So let's see what happens and sort of demonstrate the technique here. So what we do is we pick one of the equations and one of the variables. It genuinely doesn't matter. But usually it's easiest to go first equation, first variable, and then work from that, right? So pick a variable and equation and isolate. So that means put the variable all on one side by itself. So that means we're going to move this to the other side. Right, we move this term plus 2x3 to the other side. And then now we'll just divide by 2 to get this relationship. Now, we know that every instance, actually, yeah, let's do it that way. Every instance of x1, we can replace with minus x3 instead, right? Now, substitute in the remaining equations. So we just used this one. So there are 2 other equations left, right? And so we're going to go ahead and use this relationship to essentially get rid of x1. So we've got this, x2 equals 1, 3x2 minus 2x3 is equal to minus 1. So we could take this and replace x1 with minus x3. And then 3x2 minus 2x3 is equal to minus 1. Now, the reason why that was useful, we started with a system of equations that had 3 variables, right? And through this, we just got rid of 1. Right now, we've reduced it to, hey, let's just look at these 2 equations now and these 2 unknown variables. And then once we know what x3 is, we can just use this relationship to figure out what x1 is. Right? Whatever x3 is, tells us what x1 is. Yeah. Okay, now we repeat. So repeat the process. So we pick one of these equations. It doesn't matter which one. I'm going to pick the first one again. Equals 1. And we isolate one of the variables in terms of the other ones. Again, it doesn't matter which one, but I like to go just in order. Just, we do the first x1, then x2, and then so on. So we're going to isolate x2. So let's move that over and that over. Like that. All right, now we have another relationship. What does this relationship tell us? How to get rid of x2 in the remaining equations. There's only one more equation left, right? We just used this one. So this is the only one left that we can get rid of stuff in, because we already got rid of the first one too in this original relationship. We've used this one and now we've used this one. We just got one left. So substitute. Okay, so now we're going to go ahead and take a look at this equation. 3x2 minus 2x3 is equal to minus 1. And we'll replace x2 with this. Okay, awesome. Now, why does that help us? Well, we can simplify. Minus 3 minus 2x3 is equal to minus 1. Collect our variable terms, minus 5x3. Let's move that over. So we'll get 2, because flip the sign of minus 3 becomes plus 3 on the other side. 3 minus 1 is 2. And now we can solve. x3 is minus 2 over 5. Hey, that's a fraction, but look, we just found a number, right? We know x3 has to be this. But now we sort of work our way back up, now that we've just found a number, because, hey, if we know what x3 is, we can get x2. So x minus x3 minus 1 is equal to x2. That tells us that, plug that number in, minus 1, that's what x2 is. 2 over 5 minus 1. Don't worry, it's minus 3 over 5. It's a fraction. But again, tells us what that is. Now we know what x2 is, which we then can use to get x1. Well, actually, turns out we don't need x2 for this. We need this. But the point is, we have the information we need, right? x1 equals minus x3. So x1 is 2 over 5. So hey, x1 is this, x2 is this, x3 is this. And boy, that seemed pretty awful, right? Yeah, this method is terrible. It's so funny to me that in high school, this is the method that's covered, and we just decide not to talk about the linear algebra techniques, which aren't really that much less accessible and are so much cleaner. It's weird to me. Anyway, the point is, I'm showing you this technique so that if you have seen it, you'll be like, yeah, I remember that. If you haven't seen it, you can look at that and go, oof, gross. I don't want to do that. Good news. You don't. We won't do that. So on Wednesday, I'm hoping I will have enough time to at least do 1 or 2 examples for the purposes of the quiz, where we can talk about the better way of doing it. And then you will not have to do this technique, thankfully. In fact, we're going to do this example, but with the new technique, and we'll get the same answer, right? So Wednesday should hopefully be a light day. We're just going to talk about, what a matrix is and how it relates to this and how we can solve equations with it. And then I'll be like, okay, that's enough content.